Now, it was very useful conceptually to start thinking about how these three forces in this three-force member needed to be concurrent, and G, that made, then I could do this parallelogram rule, and G, 3 kilonewtons, then equal opposite, had to be opposite of the resultant of those two. Okay, great. The problem is that doesn't really help me yet too much. It's sort of helpful in my beginning thinking, but I don't really know these angles that are going on here. I know the diagonal or the hypotenuse or the magnitude of the resultant of FA and FB, but I don't know enough other information to make use of much of that. There's not a 60 and 30 kind of thing going on here. That only told me what the relative angle was between A and B. Now there is something, kind of very powerful there, in the sense that somehow then the 3 kilonewtons is directly, if I knew that angle, if I knew FA or something, I could easily come up with some orientations of things. But I don't know enough information quite yet. There's one more other aspect about the concurrent, though, that we haven't taken advantage of. We just said, oh, they're concurrent, so that means I could draw a drawing like I have down here that is somehow statically equivalent. But the big power is really back up in the original structure. And that's where if I were to come back and I would draw the lines of actions of the forces on the structure, you're going to end up with a pretty important result. And so let's do that for the link B. Let's do that for the link A. And if the three forces are concurrent, then what you really actually have to have is this third force has to pass through that point. So note that if I just kind of follow the way I had the original one drawn, where I didn't know what alpha was, note that it's not concurrent. All three are not concurrent. So 3 kilonewtons times some perpendicular distance is going to have no equilibrating moment going on here, right? Maybe that's hard to kind of visualize what's happening on the actual original structure. So go back to the free body diagram and do this. Again, it turns out to be our intersection point, right? So this 3 kilonewton force has to pass through in its line of action, and now we have some kind of crucial things going on. Even though not perfectly drawn, FB and FA have to be perpendicular to each other, right? And if you look at this line of action, this angle here, that now this is where the 3 kilonewton force actually has to be oriented, and so that's your real 3 kilonewton force and your new alpha to that. And so that's the same thing as that. And now I should know some distances, right? The distance, point A is 1 meter from B, and we have a total of a 3 meter long bar, so that's 2 meters between A to C. So that's 2 there, that's 1 there, and now we start to get some very interesting kinds of things. A lot of ways you could work this, but remember, the only thing we really want, well, we wanted to find the reactions at A and B, but one of them was to find this angle alpha. And I can now come in here a lot of different ways, maybe a lot of cosines, a lot of sines to kind of play around with this. I look at it and say one easy way to do it is if I create a right angle right there, if I knew the height, I know that's 60 degrees. I know it's from here to here, but I don't know it from there to there. Got to think more. Okay, so I've gone away and I thought about it a little bit. And I don't know if this is going to be the right final shortest answer, but what I do know is, I know there's a right triangle here that's got a 60-degree angle, and I know the hypotenuse. And so that's kind of key. So that means this side here, square root of 3 over 2, and this side there has to be 1/2. And now I could find this little piece, because that little piece, that's the 60-degree part, and so that would be 1/2 of cosine of 60, which is 1/2 itself, so that becomes 1/4, right? That's equal to 1/2 times cosine of 60 degrees. That's the smaller little right triangle that's going on here, right? So that means now I'm darn close to getting there. This little thing right there. Okay, now remember this 1 was the entire thing, so don't go crazy here. We got 1/2 times then the sine of 60, so that's square root of 3 over 2, or square root of 3 over 4. And so let me draw this in a different color to emphasize where we're at here on this triangle. That now the one that has alpha in it is that black triangle, right? And so I can now finally come in from that kind of construction, right? So I'm going to calculate alpha, and right, so looking at that triangle, then tangent of alpha opposite over adjacent, so that's square root of 3 over 4 over 2 plus 1/4, so 2.25. And so we'll have then square root of 3 divided by 4, all divided by 2.25, and then so that's 0.1924, and take inverse of tangent, and I get 10.89 degrees. Right? And that's pretty powerful and useful. I can come back in here if I really want to work this problem in maybe a very long way. I know with respect to the horizontal that the 3 kilonewton resultant has to be alpha 10.89 degrees. I know from the horizontal that FB is 30 degrees. Aha! So now I can actually pretty easily come up with that FB then is going to be then, well, there's an adjacent thing here, so 3 kilonewtons times cosine of 30 plus the 10.89, or of course 40.89 degrees, and that would be 2.27. What's our units here? Kilonewtons for that force. And then likewise, or similarly, we can then find that F sub A is going to be 3 times sine of 40.89 degrees, and we get a result of 1.96-ish kilonewtons. And there's our requested quantities that our reaction at A, okay, as in the force really in the link at A is 1.96 kilonewtons acting at 60 degrees. That was A, and B was 2.27 kilonewtons acting from the horizontal at downwards now at 30 degrees. And of course our alpha itself was the aforementioned 10.89 degrees. Woohoo!